to, well, if we take a sample of size 100, n equals 100, our confidence interval is going to be equal to our population, our sample mean, x bar, plus or minus. Okay, now we're going to put a number in here. We're going to say the number of standard deviations to the left and to the right of what we find for our mean. If we were looking at our estimate that we used to use when we first started, it would be 2 times the standard deviation. In case standard deviation for sample means is called the standard error. Okay, our confidence interval is going to be equal to x bar plus or minus 2 times 2 standard errors, 2 standard deviations for repeated samples on either side of the mean. That's going to be our confidence interval. Okay, so now we learned that that estimate is kind of bogus, right? Because that estimate is just, we're just rounding that off. That 2 is really 1.96. It's going to be equal to 1.96 times our standard error. So 1.96, we know that in a distribution, in a normal distribution, that 1.96 is based on 95% of the possible samples that we might get being within that range. Okay, so in other words, we'd call that our 95% confidence interval. Okay, if we wanted to do a 99% confidence interval, right, then we would use x bar plus or minus. Well, instead of plus or minus 1.96, we'd have to go out a little further to make sure we capture more possibilities, that we're more certain that we capture the true mean. So in that case, we'd go out to 2.58. Okay, and we can actually go to the z table as we did before and actually look these values up times the standard error. And again, what's the standard error equal to again? It's equal to standard deviation of population over the square root of the sample size. Okay, so now if I only needed 90% confidence, right, I could instead say x bar plus or minus. Anybody remember what the value for z is going to be for that? 1.6, was it 64? I think it's 64, right? Yeah. 1.64 times the standard error. Notice this is going to be a smaller number now. Standard error times 1.64 is going to be a smaller number that we're adding and subtracting from x. So it's going to be closer to the mean. So it's going to be closer in here. So our confidence interval is narrower when we're willing to have less confidence that we captured the mean, but it's got to be wider if we want to have more confidence, like 99% confidence. That number, that 2.58, makes it wider because we're multiplying how much we're going to go to the left of the value we got for the mean of the sample and the right of the value we got for the mean of the sample. Anybody who know what this number, this plus or minus number is called that we're adding and subtracting? What's a good name for that? Bingo, margin of error, right? That's a perfect name for that thing because that's the range to the left or the right that we think that the mean might be in based on what our sample was. Because that's called the margin of error. So in the margin of error, we're willing to if we let it be smaller, if we want a smaller margin of error, in other words, a smaller range, then and we only need 90% confidence, that can be a narrower range. But if we want a higher level of confidence, 99% has to be a wider range. That hence the 2.58. Okay, this is perfectly great. This is okay. The only problem with it is that what are we dealing with here? We're dealing with n, we're dealing with sigma, and we're dealing with x bar. Sample size, the sample mean, and what's sigma? Sample population standard deviation, right? Do we usually know the population standard deviation? No more than we usually know the population mean, which we wouldn't bother to do any of this if we knew the population mean, right? So there's a problem here. We don't know what sigma is. But in order to calculate the standard error correctly, we need to know the population standard deviation. And if we don't know the population standard deviation, what are we going to do to estimate the population standard deviation? Well, there's only one other thing that we can do. We use the sample that we took to calculate the standard deviation of the sample. And just like the mean, the standard deviation of the sample approximates the standard deviation of the population. So now we're going to call that, I'm not going to call that sigma anymore, I'm just going to call it SD. That's the standard deviation of the population. Now I can say my standard error is equal to my standard deviation for the sample over these samples, over the square root of the sample size, right? I can say that, no problem. The only problem now is that because I don't know sigma, I'm using standard deviation instead. I've introduced another layer of uncertainty, right? So now I can no longer assume that 1.96 times the standard error is going to capture my true population mean. I'm going to be 95% certain that it will. So just like we did before, what did we do in order to increase the certainty that we're going to capture the sample mean? We made the confidence interval wider, right? So we're going to do the same thing because we don't know the standard deviation of the population. We're going to use, instead of for a 95% confidence interval, instead of 1.96, we're going to use a bigger number. We're going to adjust for that level, that added uncertainty, by using a bigger number. Well, sometimes I may be using 2. Sometimes I may be using 2.5. Sometimes I may even be using 3. What do you think? What do you think will cause me to use a different number, a larger number, for that if I'm estimating the standard deviation using my sample? What would determine how much bigger that number has to be? Right? That something that'll help, something that affects the level of confidence that I have in my calculation for standard deviation. The sample size, exactly. The bigger the sample size is, the closer you can be to 1.96. A small sample size, you got to use a lot bigger number than 1.96. So the sample size was going to determine that. The way we're going to determine what that number has to be is we're going to use a different distribution that's based on small samples called a t distribution. That's what you guys were learning upstairs. Okay, so we have a whole series of steps that we're going through here. If we know when we're dealing with the population, we want to know what percentage of the population is less than a certain number, and we know the population mean and standard deviation, we just use the z table. When we take a sample and we want to know what the confidence interval is, if we know the population standard deviation, we can just use these three formulas depending on what level of certainty that we want to estimate the range that the population mean might be in. If we don't have the population mean, then we have to use the t-score that we are going to look up instead of the z-score. Instead of 1.96 and 2.58 and 1.64, we have to use that number, that t number, instead of the z-score, t-score instead of the z-score, and that's going to be based on our sample size, right? That's what's going to determine how big that number is. Okay, so we're going to actually put this to work now. There's a document on Blackboard called, that's number 2, lab session 6. That's exercise that we're going to be working on. Okay, you guys online okay with that? Thanks for the reminder about the recording too. Okay, good. All right, let me blow this up a little bit so we can see a little bit better. Okay. Okay, let's take a look at the first problem here. We're going to work our way into this. The mean of a population is known to be 160, and the standard deviation of population is known to be 20. Now, this is a situation where we really don't get into very much, except maybe in a census. The mean's 160. The population standard deviation is 20. What's the probability that a single observation selected at random from this population would have a value of less than 154? Okay, let's get a fresh piece of paper here. Okay, and this, we're simply dealing with a normal distribution, right? Normal distribution. Did I say it was normal? I think I should have said it, right? But let's assume it's normal. Mu is 160, right? So this is 160. We're interested in the percentage of the population that's below 154, or another way of stating it, what's the probability that we would select someone randomly from this population that's under 154? Maybe this is weight or something like that. Okay, so we want to know what percentage of this distribution is below 154. Well, if we want to do it with a formula, we can see, let's see, this is 6 below, and the standard deviation is 20. I can kind of figure out what's happening with standard deviation. If I want to be a little bit neater and actually use a formula, I can say x minus mu over the standard deviation is going to be our z-score. Okay, it's going to be equal to 154 minus 160 over 20 is 6 over 20 is minus 6 over 20 is minus 0.3, right? 3/10. Everybody okay with that? Okay, so now how do I find out what that area is? Well, I have the z-score. I go to my z-table, or I can use Excel. I'm going to use the table for now, if I can find it. Oh, actually, I have them online on Blackboard. Actually, yeah, you can probably get to them on Blackboard. I think I may have it. Grusty, see. Here we go. Okay, yours may not look exactly like this one. Depends on what you're using. So a z-score of negative 0.30 is about 38.2%. 0.3821 if you want to go that far. So the probability of my selecting a person from this population that has whatever this value is, weight, blood pressure, or whatever, blood sugar, who knows, right, is below 150 is 0.3821 or 38.21%. Okay, we're all comfortable with that, right? Nothing new there. Okay, let's go back. Take a look at the next part of this. What is the probability a single observation has a value greater than 166? Same deal, right? Greater than 166. Even without doing the math, what do you see immediately? You see immediately that that's 6 more than the mean, so it's going to be over here, right? So that's going to be a z-score of plus 0.3, right? Plus 0.3. And we know that this is going to wind up being the same area as this area is, right? If you can actually, if you did it and you used the table, you'd wind up calculating the area from here down. So you'd wind up getting 41.8 or something like that, right? But you can just see by observation that this is symmetrical to this side. This is a z-score of plus 0.3. That was a score minus 0.3. So this is 38% as well, 0.382. Okay. That's the question was what percentage is above that? What's the likelihood of picking someone above that? And what's the probability that a single observation has a value between those two numbers? Well, let's see, 38.21 plus 38.21. I'm going to use 38 and 38. Okay, it's going to be 76, right? So that's going to leave 24% of the population between 154 and 166. Okay, so we got our juices flowing here. We got something. This is something we did like probably week 3 or something like that, somewhere around there. Okay, so that's going to move on to the next step. You take a random sample from a population, and the mean of your sample, sample size. I didn't put the sample size in here, I guess. Okay, I'm sorry, sample. Oh, because I gave it to you later on. Okay, sample size n has a mean of 150. Assume the population is normally distributed with a standard deviation of 30. Calculate the standard error for samples of size n. Okay, so we got 2 problems here. One is, well, the first problem is we don't know the population standard deviation, right? So instead of using the z-score, what are we going to have to use? We're going to have to use a t-score instead. Now, I'm going to let you in on a dirty little secret now, okay? Most of the time, and I think on the last slide or the next to last slide, I think you saw tonight, somewhere around there, Professor Waldron mentioned that if the sample size is greater than 30, a lot of times, at least on your preliminary run, you probably will just assume that the standard deviation is a good estimate of the your standard deviation you get from your sample, because it's a large sample of greater than 30, that your standard deviation is a good estimate of the population standard deviation. So we're going to take that to heart, and we're not going to use the t-table right now. We're going to assume that since it's a sample size bigger than 30, we're going to assume that what we get for from the standard deviation of the sample is the same as the sigma, the population standard deviation. Okay, so let's just make that assumption. Let's break that rule for the moment and say that that's the case. So in that case, let's see, the mean is 150, the sample size is 100. Get a fresh piece of paper here. Oops. Okay, so the mean X bar, remember it's a sample, is what I say, 150. The standard deviation of the sample is 30. Oh, standard deviation. Oh, I'm sorry. I gave you the population standard deviation. That's sigma. So we don't even have to bother with that. Sigma is equal to 30. Okay, so I actually I'm got a little ahead of myself. Sigma is equal to 30, and the sample size is equal to 100. Okay, so now we have to calculate to get our confidence interval. We're going to say x bar plus or minus, okay, some value for z. I'm saying z because we know sigma, so we're going to work with z. Some values for z times the standard error. So first thing I need that standard error. What's that standard error going to be equal to? Going to be equal to the standard deviation of the population over the square root of the sample size, okay, which is going to be 30 over 10. In other words, 3. That's going to be our standard error. And what's the value for z going to be? Actually, that's the first part was just that, right? Our standard error is equal to 3. Compute a 95% confidence interval for the mean of this population. Okay, let's see. So x is going to be 150 plus or minus. Now, what is z going to be? 95% confidence interval. Our standard error is based on the population mean, population standard deviation. So I can just go ahead and use what value? 1.96, right? Times my standard error, which is 3. So 150 plus or minus, I'm going to take the liberty of calling that 6 for our purposes tonight. Okay, so that's going to be 144 to 156. Our confidence interval is going to be 144 to 156. We're 95% sure, based on this result for our sample, our random sample, we're 95% sure that the true population mean lies between 144 and 156. Okay, and we were able to use that value for z because we knew the population standard deviation, sigma. Okay, so now what if I had asked, well, in fact, let me take a look. I may wind up asking you, what's the 99% confidence interval? What changes now? 150 plus or minus 2.58, right, exactly, times 3, right? And I'm gonna call that again, just to round it off, I'm gonna call that 5, right? So now 150, I'm sorry, not 5, 3 times 2.5 is gonna be 7.5. Right? It's going to be 142.5 and 157.5. That's going to be our 95% confidence interval. Notice it's wider than our 95% confidence interval. Okay, and finally, it's going to ask you 90% confidence interval. I'm not going to bother with that one because we know that one's going to be exactly the same, except we're going to use 1.64. And it's going to be the narrow stuff. And it's okay for it to be narrow because that's the one that we have the least confidence in, right? Okay, so, okay, good. Let's take a look at the next one. A random sample of size n equals 36 has a mean of 150. Assume the population is normally distributed with a standard deviation of 30. Okay, so basically we're going to do the same thing again. So we're kind of beating this to death a little bit, but let's go ahead and do it. Okay, so we know the population stat. Let me copy this first so it's a little easier. 36, 150, n equals 36. X bar is equal to 150, and the standard deviation in this case was 30 again. Okay, now what's our standard error going to be equal to? Standard error is going to be equal to, let's see, 30 sigma over the square root of n, which is 6. This time it's going to be equal to 5. Okay, nothing's changed here. Only thing that's changed is the sample size, right? So let's see how that affects the confidence interval. First, I'm going to calculate is the 95% confidence interval. Okay, 95% is going to be x bar plus or minus. Okay, now since it's a 95% confidence interval, and since I know the population standard deviation, 1.96 again. times my standard error, which is 5. Okay, x bar is 150 plus or minus 2 times about roughly 10. So the confidence interval is going to be 140 to 160. Okay, notice that this is wider. Everything was the same as what was the only thing that was different? The standard deviation was 30 before also. The mean x bar was 30, 150. The only thing that's different is the sample size, right? So the sample size, even if we know the population standard deviation, the sample size affects our level of the range that we have for the confidence of capturing the mean. And that makes sense because we're less certain of what the mean is. If we take a sample of only 36, we're less certain that that's really the mean than if we took a sample size of 100. So that kind of makes sense. I'm not going to, you could go back now and do the same thing with the 99 and 90% confidence interval. All it would change is that 1.96. Okay, now let's go to 3B. 3B, a random sample of size n equals 36 has a mean of 150. Okay, assume the population is normally distributed. That's 3A. Hang on. Scroll up a little bit here. Okay, standard deviation. The standard deviation of the sample is 30. We don't know the population standard deviation there, so we can't calculate the standard error using the population standard deviation. We have to use instead the standard deviation for the sample. Okay, now it happened to be I made it 30, so the number's going to come out the same, but something's important is going to change here. Okay, and for the moment, I'm going to say to myself, 30, I'm going to consider that a small sample. So it's a bit over 30, maybe I'll consider a big sample. But under the 30 or under, I'm going to consider that a small sample, which means I can't use Z. I have to accommodate for the uncertainty that not knowing the population standard deviation, having to estimate the population standard deviation from the standard deviation of my sample, I'm going to have to account for that uncertainty. So let's take a look at how I'm going to do that. Okay, first, calculate the margin of error for samples of size. Let's see. N is equal to 50. Oh, it wasn't even 30. Standard deviation was 30. So it's really a small sample size. So I really have to do that. Okay, so what do I know here? X bar, I took a sample of size 15 people, and my mean was 150. X bar is equal to 150. Let's see, and my standard deviation of my sample is equal to 30. I don't know I don't know what sigma is. Sigma is unknown to us. Okay, don't know that. We don't know what mu is. Right, both unknown to us in this case. Okay, so now I want to calculate. In order to calculate a confidence interval, I have to calculate a standard error and a margin of error. Right. So my standard error is going to be equal to, well, normally would be equal to sigma over the square root of n, right? But I don't know sigma, so instead I'm going to have to use the standard deviation of the sample. That's going to be 30 divided by the square root of the sample size. Sample size is 15. So for this, we're going to have to get a calculator out. Okay, let's see. Oops, can't use that calculator. Let's use this one. Okay, 15. And square root of 15 is going to be I'm going to call it 3.9. Okay, normally if you're on an exam or you're doing homework, you're going to be a little bit more precise than this, but I don't want to get too hung up on this. 3.9. Okay, it's going to be the square root of 15. Okay, so my standard error is going to be equal to 30 divided by 3.9. Divided by 3.9 is equal to 7.7. Okay, there's my standard error. Okay, so now, in order to find my confidence interval, I need to find my margin of error, right? Because it's x bar plus or minus my margin of error. My margin of error is going to be the z-score times 7.7, my standard error. Okay, whatever this, except because I have a small sample size, and because I don't know what sigma is, I have to use a t-score instead of a z-score. I'm going to use a t-score for alpha. Alpha is the level of error that you're willing to accept. So if your level of certainty is 95%, what's the probability that you're wrong? 5%. You're 95% confident, means you're willing to have 5% chance you're wrong. Well, now I'm going to call that alpha. I'm going to call alpha over 2, right? Our level of interest, which is 0.025. That's the amount that's in either the left tail or the right tail. That's what our t-score. That's what our score is. In other words, think about when I say 1.96 represents 95%, right? It means that you have 2.5% in the left tail that's outside of that range and 2.5% in the right tail. So if I'm saying 95% confidence, right, my t-score is for a tail of 2.5%. So alpha over 2 is 2.5%. The reason why I put that in there, a lot of the tables, some of the tables will say right at the top, 95% confidence interval and give you the t-score. Some of them will just give you an alpha or an alpha over 2, and you have to think about it and say, well, the alpha over 2 I want is 0.025, right? If it says alpha, alpha's 5%, but alpha over 2. So it's a little bit tricky. You'll see when we look at the table, it's a little bit tricky, but we know that we want that for a 95% confidence interval. So when we look at the table, we'll just keep that in mind. So I need to know what that t-score is. So now we know X bar is 150 plus or minus t times the standard error, which is 7.7. Okay, so now we have to figure out what t is. So we need our t table. Okay. Now, I'm not sure what yours is going to look like. Here's the one for Agresti. I think I put that up on Blackboard most likely. Okay, so let's take a look at this. Okay, in fact, this one is handy and less confusing because it gives you both ways. Right? Some of them won't. Okay, some of them might only give you this middle bar over here, right tail probability, right? This one gives you the confidence level and the right tail probability. If you look at this 95% confidence interval, well, that means that 2.5% probability is in each tail, right? So the right tail is 2.5, the left tail is 2.5. So all you have to do is go down this column, and you know you're right because it's 95%, and the t is alpha over 2 is 0.025, half of the remaining 5%. So now, normally it's based on the sample size. Notice that depending on the sample size, as we move down here, as the sample size gets larger, what happens to the number t? It gets closer and closer to 1.96. And where is it exactly 1.96? When the sample size is infinite, when you have the whole population. Right? That's really basically what that means. So anything but the whole population or an infinite number of samples, right, is going to be something different than 1.96. It's going to be bigger than 1.96. And this is to make up for. And as the sample size is smaller, we have less confidence in our estimate of the population standard deviation. So that number gets bigger and makes the margin of error bigger. It makes our confidence interval wider. So now you'll notice that it doesn't say sample size here. It says degrees of freedom in here. Remember we discussed when we were calculating the variance, we said that we divided the sum of squares by n minus 1 instead of n, and we call that the degrees of freedom. One of the ways you can kind of look at that is, let's say you take a sample of size 1. You only got one number, so no degrees of freedom, right? That number is it. If you got two numbers, you take a sample, you got two numbers, you have a choice between two values. So you have 1 degree of freedom. You could choose one way or the other way. 3 sample size of 3, you have 2 degrees of freedom, and so on and so forth. So the degrees of freedom are basically the sample size minus 1. Okay, so in our case, sample size was 15. So the degrees of freedom is 14. So we're going to go over to our table, and our t-score is going to be 2.145 is what we're going to use for our 95% confidence interval. If I wanted a 99% confidence interval, what would I use instead of 2.145? You can see it up there, right? 99% confidence interval, what would I use going across? 2.977, right? Okay, bigger number makes the confidence interval wider. Okay, so 2.145. Let's go back to our calculation. Okay, so that t-score now is going to be, okay, oops, my connector's shot over here from too many years of dropping this thing. Okay, there we go. Okay, so it's 150 plus or minus 2.145 times 7.7. So our margin of error is going to be, let me clear this, 2.145 times 7.7 is equal to 16.51. And I'm going to put that into my memory and clear it. Okay, so I take 150 minus my margin of error, minus, let me recall, minus 16.5, and that's equal to 133.5. And I will also add, take 150 and add my margin of error to that. Oops, clearly that's not it. Plus 16.51, it's going to be 166.5. Okay, the real trick here was to recognize when you use the t-score, when you use the z-score, and which t-score you use, and so on. Let's take a look at. Let's continue with that problem and see what else it asks us for. Okay, then it asks us for a 99% confidence interval. Let's do that one. 99% confidence interval, instead of being 2.145, 99% confidence interval will be 2.998. I'm going to call 150 plus or minus 2.98 times 7.7, right, which is going to be, I'm going to clear that, which is going to be 2.98 times 7.7 equals that. I'm going to put that into memory. Let me clear the memory first. Memory plus, clear. So it's 150 minus 23 basically. It's going to be 127. And 150 plus my margin of error. Whoops. 150 plus my margin of error. It's going to be 173. Okay, not hard, right? A little confusing because you got to read these problems as you read them. They can get a little complicated. There's a homework there's homework available on Blackboard that I haven't put yet into the that self-answer thing. We'll give you the answer right away, but you can see the document. So you can start working on it until I get it active and you can input the answers. That's got a lot of word problems. It has some actual public health problems and descriptions of situations and stuff like that. And you kind of have to parse it, programmers. And I think also grammatician, how would you say that? People that study grammar. It's not grammaticians, grammatician, whatever. People that study grammar and coders have something in common. They do something called parsing, right? In parsing, like for instance, when you parse a sentence, you identify the noun, the verb, and so on and so forth. When you're coding, you identify the object, you identify things that affect the object, you make rules for it and stuff, so on and so forth. So when you have a statement in a program, if you want to understand what's going on, you kind of have to parse it into the different parts of it, break it up into parts that are understandable. Same thing with these problems. When you read the problems, you have to read it analytically. You got to say, am I dealing with a population or sample from a population? How big is the sample? Do I know the population standard deviation? If I don't know the population standard deviation, how is the sample size going to affect it? Now I know I got to use t-score. How's the sample size going to affect the t-score? Where am I going to look that up? What am I being asked for? Am I being asked for a 99% confidence interval, 90% confidence interval, so on and so forth? So you're going to have to read that and extract from all of the camouflage that the problem presents. You're going to have to extract those numbers. Sometimes that can be the hardest part because really what we're doing here is not that challenging. Sometimes the most challenging part is really applying it to a real life problem where you gotta have to figure out which of these equations and which of these numbers, what t-score, whether to apply to t-score, z-score, and so on and so forth. Okay, suppose that we want to estimate the average weight of an adult male. We draw a sample of 1,000 men from a population of 1,000,000. We find that the average man in our sample weighs 180 pounds. The sample is very large, so we assume for the purposes of analysis that standard deviation of the population is the same as the standard deviation of the standard deviation of the sample, same as that population, okay, which is 30. Okay, so now what does that tell you? I just told you that you can use the z-score there, basically, didn't I? Right? Because I told you can assume for our purposes that we know what sigma is because it's such a big sample. That's not unusual. You may have noticed that Professor Waldron gave you some rules about sample sizes and how to use sample sizes. So it's not unusual when you're working with a very big sample. Just for argument's sake, let's say I didn't say that that's true. Let's say that I told you that the standard deviation that we gave you is based on the sample, not on the population. What would be the value of t that you would use instead of z? For a 95% confidence interval, you would use 1.96. Let's see what you would use for a sample size of 1,000. So a sample size of 1,000 would be 999 degrees of freedom. Well, you want to know something? Doesn't even go up that high. It goes up to 100. Next thing's infinity. So a sample size of 100, 101, which would be 100, is already going to be down to 1.984. It's so close to 1.98, why even bother? Just use the z-score. That's the idea that if you look here, a sample size of 100 is so close to the t-value that you would use is so close to 1.96 that for the most part, when you're doing these calculations by hand, you wouldn't bother. When you're using software, when you're using Excel to calculate a t-score, there's ways to do it. If you're using SAS, if you're using SPSS, right? Maybe next week we'll play around with doing this with SPSS. When using SPSS to do this, SPSS, it doesn't matter if your sample size is 5,933 people, it's always going to use a t-score, even if the t-score turns out to be 1.9601, right? Why? Because it can. I mean, it's a machine. It doesn't matter. It's not saving any time by using anything but the most precise value that's available to us. For our purposes, because we're using calculators, Excel, and so on and so forth, it's a convenience for us if the sample gets very large. And if you notice something, once the sample gets bigger than, let's see, 95% confidence interval, once the sample gets bigger than, let's see, 20, it's, let's see, at 10, it's 2.2, 20, it's 2.1, 30 is starting to get to 2.04. It's getting pretty close to 2 as we're getting into 30. So once we get over 30, a lot of times we'll just default to 1.96, especially in our initial calculations. Okay, so if that comes up, you can kind of use that as an excuse to use the z-score. Most of the time we'll prompt you on what we want to do. This kind of prompts you, I think, a little bit into making that assumption. Okay, so now, how would we solve this? I'm not going to solve this. I'm just going to ask you. We're going to look at it analytically. How are we going to solve it? Okay, 95% confidence interval. What's the average? The average that we got was how much? 180? Okay, and what's our standard deviation? 30. Okay, so what's our sample size? Our sample size is 1,000. What's the square root of 1,000? Roughly. Anybody know? How much? No, that's 10,000. That's the square root of 10,000. 1,000. Let's see, square root is about 32, right? So we would take that's 30 divided by 32. Our standard error would be roughly 1, right? And what would we do then? We would add and subtract 1.96 times 1, because it's such a big sample size, we're going to use 1.96 to our mean. So what's our confidence interval going to be? It's going to be 179 to roughly 181. How about if we had a sample size of 100? That's still a pretty big sample size. And I told you could use the sample standard deviation as instead of the mean. Then we would multiply 1.96 times 30 divided by the square root of 100, which is 10. That'd be 3. So it would be I'm sorry, 1.96 times 1 would have been 2. You guys didn't catch me there, right? It's really 178 to 182, right? 1.96 times standard error of 1 is a margin of error of 2. So it's 2 subtracted from 180, 2 added. Am I going too fast? No? Okay, you get what I'm saying. Okay, so for a sample size of 100, it would be 30 divided by 10, right, square root of 100. So that would be a standard error of 3 multiplied by 1.96. It would be roughly a margin of error of 6. So we'd add and subtract 6 from our mean. Okay, and then finally we get to a sample size of 25. Well, we would divide by 5, right? Okay, because the square root of 25 is 5, so we take 30 divided by 5, we have 6. Problem though, now we have a small sample. So we really shouldn't use 1.96 anymore. We should use the t-score for a 95% confidence interval for 24 degrees of freedom. So instead of 1.96, we should be multiplying that value by, let's see if I got the right column here. 95% is this one, 2.064. Okay? All right. Now let's throw another wrench in here. Okay? This is too simple, so we have to make it more complicated. That's the reason for this course. A major metropolitan newspaper surveyed a random sample of 200 voters. They asked whether they plan on voting for a new bond act. 110 of those surveyed say yes, they plan to vote yes. Now, does that mean that what proportion of the population does it look like is going to vote yes? 110 out of 200. What percentage is that? 55%, right? 0.55, 55%. 110 over 200 is 0.55, right? Does that mean that the majority of people in this population are going to vote yes? It's encouraging, but we don't know the real population proportion that's going to vote yes. We only know our sample of 200. This is a point estimate, just like the mean was a point estimate. This is one number that we're using to approximate what we think the population is. But we don't know what the population is. We only know what the 200 people that we selected appeared to be, that we selected at random. Our hope is that we got a good sample, but hey, you guys have seen elections. Sometimes, they're wrong, right, when they predict this stuff, right? So we want to find out what our confidence interval is. Are we 95% sure that the majority of voters are going to vote yes? Okay, well, how are we going to know that? Well, if we go, based on our sample, we got 95%, 55% we think are going to vote yes. If we have a 95% confidence interval for what the true mean around that 55% is, we'll know whether or not our confidence interval is above 50% or if part of it overhangs below 50%. In other words, if our confidence interval turns out to be 45 to 60, well, we're not sure, we're not 95% certain that it's not less than 50%. But if our confidence interval is 51% to 59%, now we're 95% sure it's above 50%. Get it? Right? It's a way for us to tell whether or not that 55% of our sample, when we look at our level of confidence for 95% level of confidence, whether or not the true mean is still above 50%. Okay, so we want to see what that range is and see if it's above, if both ends of it are above 50%. Okay, so how do we calculate this? Well, we calculate this just as we did before. Well, we just use a different way of calculating the standard error, and that's going to be the square root of the probability that we measured times 1 minus that probability over n and take the square root of the whole thing. Okay, so we're going to use that formula now. So let's give this a try. This may make a little bit more sense when we actually work this out. If I lost you there a little bit, don't get discouraged. Okay, I'm going to call this P cap, right? P cap's kind of like a P would be the population proportion, right? That we don't know that. P cap is what our sample proportion is, which is equal to 0.55. Okay, that's kind of like our mean has a little bar over it. I'm going to call it P cap to low so you know that that's based on our sample. Okay, and our sample size was what? 200, right? Am I right about that? Right. Okay, good. Okay, so now I want to know what our 95% confidence interval is. Okay, so P cap, let's see, it's going to be P cap plus or minus, you're doing the same thing as I did before, either a z-score or a t-score. Okay, now I got a problem here. How do I evaluate this? Sample size of 200, pretty big sample, isn't it? Right? So actually, it's quite a large sample, 200, right? And we already said that, we got a big sample like that, we're going to use z instead of using t so that we can estimate it. However, when we're dealing with a proportion, we have a special rule. And that rule says that either side of the proportion has to have at least 15 people, has to be equal to or greater than 15 results. Okay, either side. Well, I had 110 people that said yes. How many people said no? 90. Both of those are over 15. Since my rule says that both of those have to be over 15, you have to have at least 15 people on this end and 15 people on this end. So your sample size is always going to be greater than 30, right? Usually substantially greater than 30. So for these proportions, I'm not going to bother with the t-test. I'm just going to use the z-score, right? Z times my standard error. Okay, let's see what that's going to be. It's going to be equal to 0.55 plus or minus for a 95% confidence interval. Z is going to be 1.96 times my standard error. What's my standard error going to be? Standard error is going to be equal to, it's going to be equal to P times 1 minus P, 1 minus P over N, and I'm going to take square root of the whole thing. Okay, so that's going to be equal to 0.55 times 0.45 over N, which is 200, and I'm going to take square root of that whole mess. Okay, I want to just check online here how we're doing there. Okay, how's the root? Did I miss you guys? Oh, no, you got, okay, there was a question, but I think it got resolved. Okay, good. It's good that you guys are online or good at taking care of each other. Okay, so let's see what this is going to wind up being. Let's get our calculator up. Okay, so calculator, let's see, 0.55. Let me clear everything out over here, memory and all this other stuff. 0.55 times 0.45 is equal to 0.2475 divided by, sample size is 200, is equal to this. And now I'm going to take the square root of that. Ironically, since it's a fraction, the square root is actually going to be a bigger number. Square root. Okay, it's equal to 0.035. It's equal to 3.5%. 0.035. 0.035. Okay, so now, what's this going to come out to? 0.55 plus or minus 1.96 times 0.0, that's roughly 2 times 3.5%, is about 7%, right? So I'm going to add and subtract 7% to my 55%. So my confidence interval is going to be 0.48 to 0.62. I'm 95% sure that the true population proportion that's going to vote yes is between 48% and 62%. Am I 95% sure that it's greater than 50? No, I'm not, because it could be 49, could be 48 and a half, could be 48, right? So had this come out to be 0.51 to 0.59, I would have said, oh, I'm 95% sure this proposition is going to pass. But now I can't be sure because there is a chance I don't have 95% confidence, right? Now let's do something interesting. Let's do this again, except for 90% confidence interval. Well, for 90% confidence interval, let's see how it works out. 1.64 times 0.035. What does that come out to roughly? See if we get. Let's see if we can see if that works. 1.65 times 0.035 is equal to about 6%, it's still not enough. I'm not even 90% sure, right? Okay, because I'm still down at 49%, 49% to 51%. So listen, this is an interesting tool. Now we have a tool that not only gives us a confidence interval, but now we got a way to kind of compare it to something else. If I know that the blood pressure of all Frenchmen is 90 because they drink a lot of wine, eat a lot of eat Mediterranean diet, their blood pressure is 90. If I'm 95% sure, if I take a sample of Americans and I'm 95% sure that the average blood pressure for Americans is somewhere between 92 and 107, right? Well, I'm 95% sure that Americans have higher, on average, have higher blood pressure than Frenchmen because they're that one value that if I knew all the exact value for Frenchmen, I have a way to compare whether or not I'm certain from my sample whether Americans are different or not. Okay, that's kind of cool, right? That I can compare this. This when we do this later on, this is going to turn into something called a one sample t-test. We're taking a sample, developing a confidence interval, and we're comparing it to a certain value, right? Most of the time, that's not what we're doing. Most of the time, we're comparing two groups. We're comparing group A to group B. And we have two confidence intervals now that could overlap, maybe they don't overlap. But in fact, we don't really use them that way. If it's one value that we're comparing to a confidence interval, we can kind of make a judgment what our level of certainty is that they're different, the means are different. But when we get to two, it gets a little bit more complicated. Okay, so the next two problems, I'm going to give, you guys are going to give that a try. And I'll read them with you. And